spring, you know, that's in some that's some damping, some internal damping or something, and we hook it up to something which is maybe time varying, which is going to push on the spring or beat on the spring. And the rate at which it pushes or beats on the spring is not necessarily related to the rate at which the spring would naturally want to go. Okay, so it's just some other rate at which you're pushing on the spring. Then now our differential equation, you know, when we set this equal to mx double dot, we have, you know, a differential equation, again a second order differential equation, but we have this extra term. So we look at it, you know, we got something like x double dot plus b over m, x dot plus k over m, x is equal to f of t. So now we have a inhomogeneous second order linear differential equation. It's inhomogeneous, right? I always forget this. Inhomogeneous means the stuff over here isn't zero. Yeah, homogeneous means the stuff over here is equal to zero. I would put that backwards. So these can be very difficult to solve. But what we're going to do is we're going to write down the simplest case of a force. The simplest case of the force would be to let the force be some magnitude times the cosine of omega t. So you just sort of push on it with some oscillatory force. So you got a spring that wants to oscillate like this, but then you start pushing on it with something else that makes it do something different.
Wouldn't that be a push and a pull, depending on what?
Yeah, it will push and pull on the thing, right? That's right. Because you get a sine out of the cosine. So, and there's some omega here, which is related to the whatever mechanical device you're using to push and pull on the thing, which may or may not have anything to do with the omega of the actual spring. So there's still the frequency which the undamped spring would want to go. So omega 0 squared is still k over m. So if the spring was undamped, it would oscillate with any given frequency omega 0. And now you're pushing on it, so it's going to have this extra term. So the idea here is that the solution, which we jump right to, you guys have noticed, by the way, that when the physics professor jumps right to the solution, it means it's really hard to get there.
Yeah, it's like 3 pages of algebra between where you are.
Right, okay, so when you see me work through something, or, you know, or Professor Devaney, Professor Arndt, you know, Professor Wade, some upper level class, we start working through something, that's because we expect you to be able to do that too. And we just go, clearly the solution is, and start writing it down, it's because it's hellaciously hard. Okay, and you'll start seeing this in books too.
Yeah, Griffiths does that.
Griffiths does that a lot, you know.
Definitely makes us do that.
Yeah, well, you know, some of us are more maniacal than others.
And he doesn't even have a beard. He really starts you
Yeah, he doesn't have a beard. He should grow one.
He feels lazy, but it's close to
Sharks. Alright.
I didn't see any sharks. They could be some. It's all recorded.
Sharks with laser beams.
Alright.
For the record, sharks with laser beams.
Alright. So we write the solution as the sum of two functions. Xc is called the complementary solution, and the complementary solution is just the ordinary old solution of the damped harmonic oscillator equation. So Xc is for no damping, or it's for damped oscillator. Damped F equals 0 solution. So it turns out that you could write, and this is actually quite remarkable that you can do this, that the solution to this differential equation with the term on this side is the solution without the term plus another function. Okay. The other function is called the particular solution. It's the particular solution for the particular function f.
Solves the non-homogeneous part.
Solves the non-homogeneous part, right. And the particular solution for this case, for f0 cosine omega t, is a over the square root of omega 0 squared minus omega squared plus 4 omega squared beta squared cosine of omega t plus delta, where beta is b over 2m omega 0 is the square root of k over m, and delta, the phase, is the inverse tangent of 2 omega beta over square root. Okay, fine. So, there it is. And the important thing to understand about this, there's two things that are important to understand. First is that the complementary part, the solution to the damped harmonic oscillator equation, goes away after a while. Right? So there's some period of time, your spring would have been going back and forth, which would just die down. Okay? So after a while, XC doesn't matter. So the long time solution is XP. So there's some early on, XC might dominate what it does, but then after a while, the damped spring part goes away, and what happens is you just get XP. So after a long time, the solution is this. What it's doing is going back and forth according to the motor. But how it's driven back and forth doesn't depend just on, well, okay, let's look at it. The angular frequency of its driving back and forth is whatever the driving force is doing. It doesn't come out to work out to be in phase. And the other thing which is interesting about this is that there's omega 0 dependence down here. So how big the amplitude of the final oscillation becomes depends on this omega 0 parameter. And the thing to notice here is that, a couple things to notice. If beta is 0, then it's possible for the amplitude, oh, A, I didn't tell you what A was, right? A is F0 over M. So, is that true? Yeah, sure, I guess so. If beta is 0 here, when omega is equal to omega 0, all of this stuff out front, which is the amplitude, would blow up. So if omega is really close to omega 0, the driven damped oscillator after a long time starts having really big oscillations. But if omega is not very close to omega 0, then the amplitude of the driven oscillation at the very long time is very small. Does that make sense?
Yeah, Tesla's earthquake machine.
Okay, so this is about resonance, right? So if beta is equal to 0,
Drives the
amplitude
frequency. It's bigger.
blows up
Oh.
at
It resonated as it's just keep amplifying.
This is the idea of resonance.
Yeah, that's what it was.
This is gonna be like really important for documenting.
Can we watch that video real quick?
RLC video. Lecture.
Yeah.
Did anyone break one?
I didn't get to watch it.
Did I?
I'll post it on the YouTube. Find it.
Narrows Bridge.
Is that bridge that
So this is a bridge they built, a suspension bridge they built in the 1940s.
You know, for a goalie.
I was gonna say, yeah, that should have gone by.
My 5-hole book.
And drop down for that one.
But I could not.
those are like steel cables. That's serious.
Yeah, so this is this is the bridge.
Oh, it's coming out.
And basically, they screwed up when they constructed the bridge. They've since learned to make bridge. This is a very sci-fi, like.
Should I go back and get the car?
Music.
It's like,
Yeah.
no, I'll just leave it there.
Please tell us the Benny Hill theme song. Please.
Oh, I like the
All the
classic
comments,
music.
all the
The
comments are about the
gravitational
guy that
electric.
left his dog in the car on the bridge.
Yeah.
What?
Yeah.
No, he went back and saved it.
Wasn't he a physics teacher too?
Okay,
Why would
so
you
the
do
bridge will
that
fall
in the
down.
first place?
Alright, so the problem is that the bridge had a natural frequency of oscillation, right? And the wind blowing by the bridge created something called aerodynamic flutter, which I don't fully understand because to fully understand it, I'd have to write down the Navier-Stokes equations of fluid dynamics and really understand the details of where it all comes from. But what I basically understand is, you know how you, if you take like a sheet of paper, or you take a kite, right? You run your kite up in the air, you take a sheet of paper out in the air. When the wind blows by it, you'll get, depending on the speed of the wind, the paper will flutter. It'll flutter in different patterns depending on how fast you go. Okay, so the local wind was at the right frequency so that the induced vibration was at the resonant frequency of the bridge.
I don't understand why you didn't just drive a car to the bridge. Right?
Because back then cars didn't have reverse.
Back after they had color film, they still didn't have reverse.
Alright,
It
so
was all in black and white. You might get people-
the idea here is a resonance idea. There have been a number of other famous examples of this. The old suspension bridges, marching armies used to drop out of step when they walked across the bridge because they would worry that if they were marching at the right pace, they would set up a resonance in the bridge. And they actually screwed up, and a bunch like 400 people died in France in the 1800s because of this. Maybe we're doing this, and maybe not. And then one of the other interesting examples was that they built this new footbridge in London like 5 years ago, and they had to go back and correct for this. So it's like idiots. People didn't, obviously not business majors.
Architects.
Yeah. Yeah.
How would you correct for it?
I don't understand the details of this, but I think it has to do with how you connected the sections of the bridge together. There are ways to deaden vibrations that would come through the bridge depending on how you bolt the thing together and what you allow it, where you allow it to be flexible and stuff like that. Stuff like that is usually what I say when that's about all I know.
Stuff like that is what happened between this equation.
And then a miracle occurs, and
Alright, so if we define the amplitude D
Stuff like that.
to be A over the square root of omega 0 squared minus omega squared plus 4 omega squared beta. And we want to know where D is a maximum. So we take d omega and set it equal to 0. And you get some algebra, and basically the important term is going to be the derivative of the bottom, right? So you're taking the derivative with respect to this omega, right? So you're going to have minus a half a over all this stuff to the 3/2 multiplied by the derivative of this. The derivative of this is going to be twice omega squared minus omega 0 squared minus omega squared times omega plus 4 beta squared. And what you come down to is, if omega is equal to the square root of omega 0 squared minus beta squared, then D is maximum. Details are in the notes online. Okay, and if D is a maximum, then so we see that there's a particular omega at which you get the biggest amplitude. And again, if beta is 0, then the amplitude is infinitely big. So you can define something called the Q factor. Q is omega over 2 beta. Omega resonant. And you call this omega omega r. So omega r is the resonant omega. Omega is how much you drive it at. So if you drive it at the resonance omega is omega squared minus beta squared square rooted. The Q factor, and again, you know, this is one of these things that people who build lasers worry about this. People who build any sort of system where you want to keep it propagating, you know, think about this. So if you are thinking about a spin system, a quantum spin system, and you want to talk about how well you can sustain, you know, your state, you would have a Q factor for that. So it shows up all over experimental physics. It's basically a statement about how able you are to maintain, you know, sort of a resonant state. Does that make sense?
And if you want a good grade on the RLC lab and experimental,
Yeah, this
learn
is
what this is
everything
right
that's
now.
on there. Everything. So.
Alright.
I wish I took this course before experimental.
There you go.
It's just differential thing.
What else can we say? We're useful for experimental. I think that's why Professor Definitely keeps us around. So. He can't teach all the classes, and we're useful to mention certain things. That's the way you guys should all view physicists. Theorists are only good for the fact that the experimentalists need us.
Because they don't have time to teach because they're experimenting.
Yeah.
That's what they tell you anyway.
Alright, people good?
What's
Actually, you stay in the
omega
hall.
r equal to again?
So omega r is the resonant frequency. And the resonant frequency is the frequency at which the amplitude of your particular solution is the biggest. So here's my particular
Okay.
solution. I'm going to know what value of omega makes XP have the biggest oscillations back and forth. And the value of omega is the resonant frequency, which is omega r. I find the omega r by taking the derivative of the amplitude, all the stuff out front, with respect to omega, set it equals 0, solve for omega, right? And that's what you get. Alright? And so the formula is, you know, omega 0 squared minus beta squared. And this sort of makes sense, right? If there's no damping, what frequency ought to drive the thing at? The frequency it wants to go by itself. Okay, so if you don't have any damping, you want to drive it at the frequency that it would naturally go, and then you get a runaway solution. Okay? That makes sense? Yep.
Isn't the Q also like the frequency over the frequency range within the 3 decibel level, something like that?
That would sound reasonable. But that's
Because
not
like you
only-
can actually get Q just by looking at like the graph that you get.
Yeah, that I would believe. That I would believe, yeah.
That's how we got Q.
Yeah.
Alright. So it's about 1250. I would like to suggest, okay, so a couple things about chapter 3. There are all sorts of interesting things in chapter 3 to look at. There are sections on RLC circuits. There are other sections on, you know, more details on damping, more details on other stuff. But the stuff I've talked about is the stuff I'm going to test you on. Alright. Some of the homework involves sort of playing through the equations. But the real thing that I really want you to be able to do are these damped harmonic oscillator problems. So what I'm going to suggest that we do is have you do a damped harmonic oscillator problem now. The other option would be for us to do a homework problem. So have people done problem 1A, 1B? Who's done 1A and 1B? Okay, we're doing 1A and 1B. Okay? So, all sound things. Okay, so 1a is a first order differential equation. 1a, don't worry about it. Let's do 1b. Why do I have 1b being bad? That's got to be a dumb problem. Well, that's fine. We can do it. Why is 1b a dumb problem?
Because dy t is just separable. Because you're just taking the derivative of that with respect to y. It's y over.
Because you're asking for boundary conditions on x and there's y's.
Well, oh yeah, that's dumb too. Yeah, gosh, this is particularly dumb problem. Okay, is this, what physical system is y double prime minus 6y prime plus 2y equals 0?
Force oscillators.
No, that's the simple harmonic. Because it's linear, homogeneous. So your physics joke was right.
There's something wrong with the 1D. If it was to be a damped harmonic oscillator, there is something wrong with it.
Oh, yeah. The negative sign?
Yeah, this sign's wrong. So this is not a damped harmonic oscillator. Need a plus sign here for it to be a damped harmonic oscillator. Now the math's going to be the same. But you shouldn't expect it to die off as t goes to infinity. Right, it's going to presumably blow up as t goes to infinity. The math will be the same. So let's do that one. And we want to do it subject to y of x equals 0 is 1 and y prime is 0.25.
All right.